This video is the first lesson of my 10-part series on Gauss's arithmetic investigations for the Modern Math Academy course called Introduction to Modern Mathematics, Part 2. This is part of a 4-part course covering Euclid's Elements, Carl Friedrich Gauss's arithmetic investigations, naive set theory, and model theory. If you'd like to gain access to the other 9 lectures on Gauss, or the courses on Euclid, set theory, or model theory, please visit courses.modernmathacademy.com. Welcome to Intro to Modern Math Part 2, Gauss's Disquisitiones Arithmeticae. This is Lesson 1 of a 10-lesson course, which is part of a 4-part series on the Introduction to Modern Mathematics. And there is no better place to start looking at modern mathematics than this particular text. In English, this would be read Arithmetic Investigations by Carl Friedrich Gauss. This is a book that has had a monumental impact on all of mathematics. It was written by a 24-year-old Carl Friedrich Gauss, and I would like to begin this course to motivate it, trying to answer the very simple question, why should we study Gauss? This book came out in 1801, which is more than 200 years ago. Why should we read this old textbook? So first of all, who is the author? Carl Friedrich Gauss is often referred to as the Prince of Mathematics. 1801 was when this work was published, although he had been working on the results in here for many years. He was 24 years old when this textbook came out. I'm going to spend the rest of this lesson giving you 4 really good reasons why you should study this book. Reason number 1. Gauss was a singular genius. Here is a picture of Gauss on the money, a Deutschmark from Germany. He is probably the greatest mathematician to ever live. Personally, he's my favorite mathematician, but it's very difficult to argue that he's not number 1. He was a singular kind of genius on his own pedestal. Carl Friedrich Gauss was born in 1777 and died in 1855. He got his PhD at the age of 22 in the year 1799, and his PhD dissertation was the first proof ever of the fundamental theorem of algebra. Now, that is a crazy PhD thesis to have. He ended up proving it in 4 completely different creative and conceptual ways throughout the rest of his life. But already at the age of 22, his PhD thesis is, for lack of a better word, fundamental. This is one of the most important theorems in math, and this is the crowning achievement of what everyone learns in high school. The idea that every polynomial has at least one root over the complex numbers. And this is when he's 22. Okay, when he's 24, he publishes Arithmetic Investigations, and in this book, he was the first person ever to prove a result, which we will describe later, called quadratic reciprocity. He ended up proving this 6 different ways throughout the rest of his life. In this book, Arithmetic Investigations, he not only proves quadratic reciprocity, but he solves completely a 2,000-year-old Euclidean geometry problem. Again, at the age of 24, he has solved a 2,000-year-old problem, proved the fundamental theorem of algebra, and proved quadratic reciprocity. He doesn't just get all of his good work out at a young age. His entire life is filled with unbelievable achievements in mathematics, in physics, and inventions, and astronomy. He, later in his life, after he died, when we pried open his office and searched through his books, we found that he actually had invented non-Euclidean geometry. In part 1 of this 4-part course, we discussed Euclidean and non-Euclidean geometry, and Gauss is one of the inventors of non-Euclidean geometry. He was also asked once by a king to measure the area on the side of a hill. And because hills are not flat, they're not Euclidean. You can't just multiply length times width to get the area as you would with a rectangle. And so what does he do? He creates differential geometry for surfaces, an entire field of math, and comes up with the fundamental ideas and definitions of Gaussian curvature. He also was an astronomer by training, which required that he get really good at lots of statistical methods and calculations. He's also well known for the normal distribution, which should really be called the Gaussian distribution in statistics. If you study any physics, you will learn about magnetism and Gauss's law, which has to do with flux, which is a surface integral. So Gauss's day job was actually as an astronomer. He did math at night and astronomy during the day, as a fun little pun. He became very famous, not for his mathematics, but because he, using very little observation, his mathematical prowess allowed him to predict the appearance of a comet, which, kind of just proves how mathematics is really a form of magic predicting the future. He also was hired and created an algorithm to calculate Easter for the Catholic Church. The holiday of Easter is not set on a particular day. It is the first Sunday after the first full moon, after the equinox. And so calculating this requires serious astronomy. And that was Carl Friedrich Gauss's day job. He was an astronomer. And so he calculated Easter for the Catholic Church, which they still use today. Another one of his famous inventions is the least squares method of approximation. But he didn't just do things with the mind. He invented things in real life. He was hired as a land surveyor, as I mentioned before, where he invented differential geometry. He created a tool called a heliotrope, which is used to measure lands in surveying. He was also the co-inventor of the telegraph, which was used to communicate over long distances. It's impossible to list all of his achievements because you would actually need to know quite a lot of math to really get into what this genius, Carl Friedrich Gauss, was up to. But he's not just remembered for what he accomplished. Carl Friedrich Gauss is also remembered for his style. Every line that he writes was incredible, perfect, concise, and ripe with ideas. Someone to compare him to would be someone like Mozart, although music and math aren't completely dissimilar. They aren't completely similar either. They're both artistic in a way. Mozart was famous for never making a mistake. His music was perfect. He would sit down and write entire symphonies with a pen without ever touching an instrument. And his work is flawless. And in that regard, I would like to compare him to Carl Friedrich Gauss. Now, it's impossible to say that Gauss never made mistakes, because most mathematicians, when they publish their work, all of their bad ends and ideas that led to nowhere are erased. But every line of Gauss is methodically premeditated. And he didn't just want to have a concise idea. It wasn't about saving paper. Gauss's work, Arithmetic Investigations, is a work of art. He put a lot of effort. His motto for his life was few but ripe. He was known for not publishing every single thing that he did, Many of the things he did, like non-Euclidean geometry, were kept private, but everything he put out was unbelievable. His writing was not pedagogical, written to make it as clear to the uninitiated. His work isn't easy to read, but it is unbelievably enlightening. It is written as if he's trying to preserve a perfect sculpture or artifact. He didn't just want a haphazard proof. He wanted a proof which was like a lightning strike. It was a magical piece of art itself. The world was not ready for a lot of his work because his mind was just so great. Non-Euclidean geometry was something that Gauss understood was not going to be well received. And so he was actually dedicated to finding some kind of empirical basis for non-Euclidean geometry. And until he could find that, he just continued working on it and kept it on his shelf. So Gauss was not just a mathematician. Gauss was a mathematician's mathematician. So I'd like to share with you some quotes from some very, very famous mathematicians as well. If you don't know who these people are, these quotes won't really impact you as much as they should. All of the mathematicians that I'm going to be quoting here are in a category of their own, and yet they all still revere Gauss as the premier mathematician's mathematician. So Peter Dirichlet, who lived in 1805 to 1859, said the following: Gauss's arithmetic investigations opened my eyes to the beauty of number theory. I carried it with me as a sacred text. This is very similar, as we saw in part 1 of our series, that Abraham Lincoln walked around with a copy of Euclid on him at all times. Dirichlet did the same. Dirichlet is an extremely famous mathematician and number theorist. A contemporary and someone whose work Gauss was familiar with when he was first starting was Pierre-Simon Laplace, who says Gauss is the greatest mathematician of our time. His works place him on the same level as Newton and Archimedes. Now, if you're going to argue about who is the greatest mathematician of all time, you will immediately have Archimedes, Newton, Gauss, and Euler. Leonhard Euler was a Swiss mathematician who is, there's no one to compare Euler to other than Gauss. But as you can see here, immediately in his day, his contemporaries are saying that he is the same level as Archimedes and Newton. Discussing who's the greatest mathematician is for a different time and place, but as you can see, his contemporaries recognized his absolute genius. Bernard Riemann, another one of these absolute titans of mathematics, was actually the student of Carl Friedrich Gauss. So you might think that there's a little bit of bias in this, but Bernard Riemann, a genius, it takes one to know one, as they say. And Bernard Riemann says, the works of Gauss are a treasure trove. To penetrate them is to uncover new worlds of thought. I will explore this particular idea in detail at the end of this presentation. Another very famous mathematician, Felix Klein, says, Gauss stands at the pinnacle of mathematics, a colossus whose ideas we still strive to fully comprehend. Both of these quotes are really getting at something I'm going to talk about later. To read this book is to see into the future. We still don't know what treasures are hidden in this 200-year-old book. It's quite unbelievable. Another very famous mathematician and physicist was Hermann Minkowski, who says, Gauss's genius lies not just in what he proved, but in what he saw and left for us to discover. The ideas in this book have been developed for over 200 years and are still active and budding fields of research. And our last quote here from Sophus Lee says, Gauss was not only the greatest mathematician of his century, but one whose ideas have an inexhaustible richness that continues to unfold in every direction of mathematical thought. So this is very high praise from a number of very, very important mathematicians. And again, if you don't know who these mathematicians are, you should look them up as well, because that will help you understand the level of appreciation to have for Gauss. He was a mathematician's mathematician. My second reason why you should study Gauss is that this is a singular introduction to what I am trying to explain here is modern mathematics. When you read Euclid, you are reading a book that is more than 2,000 years old. It has a different style and different ideas about what numbers are. Gauss also has that. Gauss is still not living in modern mathematics, but he created modern mathematics with this textbook. And so I'd like to explain why you need to read this book, because this will show you what modern mathematics became. Was all inspired by this text, I would argue. Mathematics looks different after Gauss. It did take another 100 years after this book, Arithmetic Investigations, for the subject of mathematics to really become what I am trying to tell you is modern mathematics, which you should understand by the end of this 4-part course. But if you look back now that we live in the world of modern mathematics, it's impossible to look at a single page of Gauss without having your jaw drop at how influential and how deep and penetrating these ideas are. In my opinion, this is the second most influential book in all of mathematical history. Now, people can argue that Newton's Principia Mathematica was extremely influential, and I wouldn't argue against that. But I don't think that it had the same impact on the style and methodology of math. Newton's work is groundbreaking and has opened up avenues of science and technology, but it didn't influence the way we think and write about mathematics in the same way as Euclid or Gauss. Gauss's work, Disquisitiones, was responsible for cementing the idea that math has different fields or branches of study. It separated number theory as a science of its own. Gauss called this new science the queen of mathematics, to which he was, of course, the prince. At the time, math was not what we think of it as today. All of math was really just a set of tools to solve very particular problems. They could be geometric problems, arithmetic problems, or problems of astronomy or motion. And you would use math to solve these problems. But mathematicians had a very difficult time grappling with what this textbook did. It is because of this book that we now think that math is separated. In general, all of academics were natural philosophy. There was only one PhD available. The PhD was in natural philosophy. But in the 1800s, math and science and the academy starts to hyper-specialize and separate themselves off into chemistry, physics, biology, math, etc. But this book began to split mathematics itself into several different fields of study. For centuries, mathematics was about solving problems, and the techniques were used, but the tools that mathematicians used were a means to an end. When Gauss publishes this book, people began already to distinguish between pure and applied mathematics, and Gauss's work seems definitely on the purer side of that. But this book was so exhaustive and specialized into such a small, tiny niche field that this pushed others after him to do the same with the works that they were doing. This wasn't just a few number theory problems being solved. Gauss was meticulously and methodically developing a field of math, which has interesting problems and techniques and solutions all of its own that have nothing seemingly to do with anything else. And this influenced all of mathematics. Now, the tools that mathematicians use to solve problems become the objects of study themselves. Gauss invents what is called modular arithmetic, but this isn't just a cool way to reprove old theorems of Euler and Fermat. Modular arithmetic is an object of its own, with its own intrinsic mysteries and problems, worthy of solving themselves. Another example would be the use of what are called special functions. In the 15, 16, 17, and 1800s, mathematicians found some really, really interesting functions which were used to prove all kinds of fantastic and amazing results, but they kind of appear out of nowhere and are just these gigantic hammers that they bash problems with. But after Gauss, now we study these things in and of themselves. So modular forms are functions which had appeared throughout much literature, but now today we would just study them outright, the study of modular forms versus the use of them. Similarly, there's an entire theory of so-called elliptic functions which are used to solve unbelievably difficult problems, but now there's something that we would study in and of themselves. We are now studying the tools that mathematicians use, not just solving problems with them. After Gauss, mathematicians following him try to systematically lay down the foundations of their subjects. For instance, his student, as I mentioned, Bernhard Riemann, his highest degree in Germany after the PhD, called a habilitation, was on geometry. And Gauss, being a master geometer, gave him the challenge of extending his results of differential geometry. And Bernhard Riemann's work here is what we today would call Riemannian geometry. This lays down the foundations of geometry itself. What does it mean to have a geometry or to do geometry? Well, it means that you have to have distances and you have to have angles. But what does that mean? Riemann publishes a work which allows us to do geometry in any dimension, in any shape, in any dimension. It is truly foundational, and clearly he's influenced by his advisor. Also in the 1800s, we have calculus being foundationalized. Augustin Louis Cauchy and Carl Weierstrass founded what we today call modern analysis and calculus. The ideas of calculus in their seminal form appear with Newton and Leibniz in the 1600s. That's correct. However, their foundations are philosophically sketchy. Through the use of mathematical ideas called infinitesimals, theologians and philosophers did not like that. And so, in the 1800s, we have the notion of a limit from Augustin Louis Cauchy and Carl Weierstrass, again, setting the foundations of calculus as a separate branch of its own, worthy of study for its own sake. And similarly, in the 1800s, we have Évariste Galois a young French revolutionary who died in a gun duel, leaving 4 manuscript pages that changed math, as well as Richard Dedekind, who was the very first person to teach Gauss his work in a university setting, and the very famous mathematician David Hilbert. They all laid down the foundations of modern algebra and algebraic structures. And there's no way of understanding what's going on in modern math without looking at Gauss himself, because he lets everyone know what this is supposed to look like. Okay? So math looks different after Gauss, but not just that. The fundamental methodology of how to study mathematical objects is present in Gauss in very important ways. Gauss uses fundamental objects called equivalence relations. And he uses this to define objects, but also to study objects up to an equivalence. And that equivalence is determined by an invariant. So most people in a high school algebra class will learn about the discriminant of a quadratic equation. Gauss uses this to study objects up to equivalence, and this is the beginning of something called invariant theory. This is an extremely important methodological aspect of Gauss's work, is that really you don't want to just study a particular object, but all objects that are equivalent to them in a certain way. I'm not claiming that Gauss invented this. He may not have, but the fundamental idea of studying equivalence classes of objects is present here in a very explicit way. And explicitly, he does this in book 1, where he invents modular arithmetic using equivalence relations. And in book 5, where he studies quadratic forms and defines them up to equivalence by an algebraic invariant. So that's what's explicitly going on. Now, implicitly, and this is what is so difficult to get across to the uninitiated reader, is how much math is underneath what's going on with Gauss, or above, however you choose to think about it. In this book, Gauss is laying down the foundations of so many different branches of math that we would today separate these. But implicitly, he is doing ring theory, group theory, field theory, Galois theory, combinatorics, quadratic forms, complex numbers, arithmetic geometry, class field theory. The more math you know, when you go back and look at this text, it boggles the mind. How could someone who did, living in the 1800s, have stumbled upon such a fruitful thing? I mean, it truly is unbelievable. Everything that Gauss does in this book has been picked up and expanded upon over the last 200 years. And even some things it took over 200 years for people to realize, which we'll talk about at the end. The third reason to study this book is just the sheer profundity of the results themselves. The things that Gauss is able to prove are just truly unbelievably deep and beautiful and elegant. This is the highest order of mathematics. When people say that math is beautiful, people often don't know what that means. And if you want to know what that means, this is a great book to see some true mathematical beauty. What did Gauss prove in arithmetic investigations? Well, he proved hundreds of things, but I want to focus in on 2 very particular results. One of them is, as I mentioned before, quadratic reciprocity, which we will prove in this course. In lesson 10 of this course, we will prove quadratic reciprocity with Gauss's proof from section 4 of this book. In section 7, he proves something on the constructibility of regular n-gons. This is the 2,000-year-old Euclidean problem that he puts to rest. And so I'd like to, in the time we have left, try to explain what exactly is going on here. What did Gauss actually prove here? So let's start with quadratic reciprocity. This is something that was originally conjectured by Euler and Lagrange before him, but Gauss was the very first to prove this statement, which I'll explain later. As I mentioned, he came up with 6 unique proofs of this in his lifetime, each of them offering a completely different insight into something much deeper. The proofs that he uses are not just standalone proofs that get thrown away. The proofs motivate much deeper proofs of much deeper facts much later. Quadratic reciprocity is the second most proved theorem in all of math. It's difficult to explain what it is in modern notation, so I'll try to explain what it is as simply as possible. Most people have never heard of quadratic reciprocity, and so they're even more shocked to find out this is the second most proved theorem in all of math. The number one, of course, being the Pythagorean theorem, which Euclid has, and we proved in the part 1 of this 4-part course. The Pythagorean theorem has 350 proofs, and the quadratic reciprocity is 200. So that's not even a close second. So this is a very technical thing to explain and to really intuitively understand, but I will tell you what it says. But this became the blueprint for the next 200 plus years of number theory. So what does this say? Usually it is phrased in terms of modular arithmetic, which Gauss invented, but I'm going to try and circumvent that. Quadratic reciprocity has something to do with the following. If you choose 2 prime numbers p and q, the question is, can you find integers x and y such that x squared is p plus a multiple of q and y squared is q plus a multiple of p? So it might seem weird and random and who cares? Well, and I haven't fully stated the theorem to state when you can and cannot find such solutions is the full statement of quadratic reciprocity. But in a sense, it has to do with this. You pick 2 primes, p and q. Can you find 2 squares, which one is p away from a multiple of q, and the other is q away from a multiple of p? So this is what it's about, which it doesn't seem that deep and profound when you think about it this way. We'll understand this much more intuitively by the end of the course. But this is what it says. It has something to do with how you can find solutions to this. Or not. Gauss called this result himself his golden theorem. And mathematicians, again, have spent 200 years extending this result. This shaped the entire development of mathematics in number theory and algebra. For instance, you can go to Wikipedia and look up so-called Dirichlet characters, class field theory, art and reciprocity, Galois representations, the Langlands program, and the recently proven the Taniyama-Shimura conjectures, and so much more. This is the beginning of modern number theory, period, is understanding this statement and how to generalize it. Now, something that's a lot easier to think about, especially after our Euclid course, is what Gauss proved about constructing polygons with a ruler and compass. So as we saw in the previous course, Euclid was only really interested in what you could do with a ruler and a compass. And so here is the question. Find a procedure by which you can use a ruler and compass to construct a polygon with equal length sides inside of a given circle. This is what Euclid is preoccupied with in Book 4, among other things. He proves that you can construct an equilateral triangle inside of a circle. This is proposition 2. He does it with a square, which is proposition 5. He does a hexagon, a 6-sided figure, in proposition 15. And Euclid is also able to do a 15-sided polygon in proposition 16. And so this naturally leads us to a question. How can you construct every possible n-gon? Why did Euclid only succeed with 3, 4, 5, 6, and 15? After 2,000 years of mathematicians trying to do these problems, one begins to wonder, is it even possible? So one thing that Gauss does is he proves that 17 is possible. But what's even more amazing is that he doesn't actually construct one. He indirectly proves that a 17-gon is constructible with ruler and compass. It actually took about 80 more years. It took about 90 years, In 1893, H.W. Richmond actually found a compass and ruler construction to create the 17-gon. But Gauss did not just prove that 17 is possible. He proved that 19 is impossible. He classified the problem completely. He ended this 2,000-year-old problem by telling us exactly which n are possible. This is unbelievable. Most people just learned that he proved the 17-gon was possible, but he actually solved the problem completely and told you exactly which ones can and which ones cannot be constructed. We will explain more about this in the next video, in part 2, or lesson 2 of this series. But the idea is actually really simple. It has to do with these following formulas. We will explain this more with pictures and more time and explanations in the next lesson. But the idea of which n-gons can be constructed has to do with formulas like these involving square roots and imaginary numbers. It's an absolutely genius idea to figure this out, but the execution itself, to really understand how amazing Gauss was, he wasn't just smart. He was powerful with his pencil. So Gauss came up with the following formula. He didn't write this formula down himself, but this is the essence of Gauss's proof. Gauss showed that this formula exists. So this is I'm sure most people staring at this are just going to have, their brains fall out, right? This is crazy to look at. What are we even looking at? Well, this formula proves that the 17-gon is constructible with a ruler and compass. Crazy. But again, Gauss proved that 19 is impossible as well. And this has to do with something called Fermat primes. A Fermat prime is a prime number of the form 2 to the n plus 1. Not all numbers like this are prime. In fact, Euler, who I mentioned before, is one probably comparable only to Gauss. Euler actually found that not all of these numbers are prime. So this insight of Gauss explains why Euclid was able to do what he did. Well, what is the number 3? The number 3 is 2 to the 2 to the 0 plus 1, a Fermat prime. 5 is 2 to the 2 to the 1 plus 1, a Fermat prime. 17 is 2 to the 2 to the 2 plus 1, a Fermat prime. But 19 is not. Gauss also proves that a product of unique Fermat primes is constructible. And you can also multiply by any power of 2. So 6, why can Euclid construct 6? Because it's 2 times 3. Euclid can also have constructed 12, since it's 6 times 2, or 24, since it's 12 times 2. But also, Euclid was able to come up with 15. Why? Because 15 is 3 times 5. So this is absolutely amazing. Gauss has classified, he's put a nail in the coffin of this 2,000-year-old Euclidean geometry problem, which countless people wasted hours of their life working on. But there's still some mystery. Not all of the work has been done on this problem. Are there infinitely many Fermat primes? This is still an open question in math. I recommend thinking about this for a little bit of time, but don't spend too much time thinking about this because this is an open problem for hundreds of years at this point. So Gauss proved, again, many things in this text. But there are 2 specific results that I think just most people need to know. Why should you read this? Well, you can learn about quadratic reciprocity, the very first proof of quadratic reciprocity, with an absolutely genius proof. Similarly, you can see a young 20-something Gauss solve a 2,000-year-old problem. This is what made him famous in the mathematical community. He became famous in the scientific community for predicting a comet, but this is what set him apart. And this result is what made this publication so famous. Mathematicians said, yeah, it's cool that he did everything else, but this is what put it in a category of its own and is what made people really contend with the power of what he was doing. He invented modular arithmetic. Yeah, that's cool, but then he uses it to do something. It was somehow justifying everything else in the book that he was able to use it to achieve this result. And so it's just absolutely amazing that you can learn these 2 great facts by reading one book. Finally, my last reason to study Gauss is that this book is littered with hidden gems revealed centuries later. As Gauss says, few but ripe. There are a handful of mathematicians like Gauss whose intellectual gaze was so penetrating. The only way to understand this is to compare him to another famous mathematician named Ramanujan. Ramanujan was an Indian mathematician who was completely untrained by Western standards, but was still somehow able to see mathematical results so deep and thought-provoking that most mathematicians just didn't believe him. And he had all of these personal notebooks where he would keep like a mathematical diary. And to this day, mathematicians are continuing to read Ramanujan's personal journals, looking for gems to make their own career off of. One line in Ramanujan can become your entire mathematical career. Some mathematicians have such insight that the things that they think about, many people will look at them and be confused and think that they're not interesting. But I highly recommend that you disabuse yourself of that silly notion. The mathematician John Tate, who's very famous in number theory, from 1925 and died recently in the year 2019, he spent most of his career extending Gauss's work. And he was doing some very sophisticated math called K-theory. So in popular culture, people will say it's not rocket science. Well, in math, we say it's not K-theory. K-theory is an unbelievably difficult branch of math. And John Tate was doing some calculations for what's called K2 of the rational numbers and realized that, his proof was just inspired and lifted from Gauss's work in this textbook. This is more than 150 years later. The ideas in this textbook are being used. Also, Section 5 of Disquisitiones, Gauss does something very weird that no one ever did after him until the year 2004. Gauss defines something and does a lot of really interesting work with it, but nobody else touched this subject. And by picking back up this idea, Manjul Bhargava, in his PhD thesis, was able to achieve the Fields Medal, which is the highest award in mathematics. Let's try and explain this a little better. In section 5, Gauss studies what are called binary quadratic forms. These are polynomials of degree 2 with two variables. So something like ax squared plus bxy plus cy squared. He gives a way to in a sense, multiply these without just directly multiplying them. It's called a composition law, to take two quadratic forms and create a new quadratic form. Mathematicians studied this and were able to prove many, many, many important results, but they never extended or generalized this phenomenon. Until Manjul Bhargava, who is here, on a return home to visit his parents in India, he took a year off of his PhD under Andrew Wiles and opened up a copy of Gauss. And as the story goes, he was playing with a Rubik's Cube and had a eureka moment and went on to define 14 new composition laws for higher degree quadratic forms. And it's an extremely powerful tool that he developed. And again, this idea that Gauss had that was left untouched by mathematicians for 200 years gets picked up again and becomes a monumental achievement and result in number theory. So, in a sense, the overwhelming majority of mathematicians are really just riding the coattails of giants like Gauss. Reading his book allows us to join them in following the trajectory of one of the greatest minds to ever grace mathematics. And so let's start actually looking at this text and talking about what's inside of it. I hope that this has inspired you, that this is a text worth reading. This book is very dense. It's originally written in Latin, and so even translating it into English, it's still very technical and very dense. This is much harder to read than Euclid, and it doesn't have many fun pictures to follow along with. But we'll be going through this book using modern ideas and modern notation, which will allow us to finally begin our journey into the wonderful world of modern mathematics. If you enjoy this content, make sure to like, share, comment, subscribe, and hit the bell for notifications. If you want to take your knowledge of math to the next level and/or join a community of math lovers, please head over to courses.modernmathacademy.com to become a member of the Academy and start learning today. From me, Dr. W.